Okay, so in this section, this is called the derivative as a function, all right? And what we're going to do is we're just going to look at the derivative of a function. We're going to be able to graph a derivative given its functional curve. We're going to look at other notations, in other words, other ways to write derivatives. We're going to look at when can a function fail to be differentiable. And then finally, we're just going to look at the relationship of higher derivatives. Mathematically, like computationally, not a lot in this video, so this video should be, relatively short compared to all the other ones. It's the next video that's going to be really, really, really in depth. Okay, so for this first example here, I graphed f of x equals x to the third minus x. Now, there are two extremely important points. In fact, we call them critical points on this graph, and they are right here and right here. So I'm going to go ahead and just tell you that the derivative of this function equals 3x squared minus 1, okay? Now, here's what I know about this, okay? I know that if I were to take this derivative and set it equal to 0, okay? And this is a little bit beyond what we're doing right now. Like, we will be doing this in a little bit, but not right now. But if I were to take this derivative and set it equal to 0, what this is telling me right here, all right, is we want to find the x values where our derivative is equal to 0. Now, if you recall from the previous section, the derivative is the slope of the tangent line. So this word, right, derivative is slope of tangent line. So what this is telling me here, this picture, is that at this point, I'm going to call this x1. This will be x2. So at this point right here, called x1, comma, f of x1, we have a horizontal tangent line. And at the second point, x2, comma, f of x2, we have another horizontal tangent line. So what we can do with this information is we can go ahead and we can use this and we can plot a graph of our derivative. All right. Now, I'm not going to do it yet because there's some other things that I want us to kind of go over. But just know that at x1 and x2, we have a derivative that is equal to 0, which means the slope of the tangent line is equal to 0 at those 2 points. Now, let's look at the interval before. I'll leave black on. Let's look at the interval prior to x1. So what I'm going to do here is I'm just going to go ahead and just lightly, just kind of like draw like just a dash line right up here. So this is going to be the interval from negative infinity all the way up to -1. Now, if I were to take any tangent line within this interval, all my tangent lines would look like this. There's one tangent line, here's a second, here's a third, but most importantly, all my tangent lines, so my derivative, is going to be greater than 0, which means they're all positive. So all the slopes of my tangent lines from negative infinity all the way up to -1 are all positive, okay? Now, in between x1 and x2, so I'm going to do the same thing with x2 here. I'm just going to lightly kind of just draw like a dotted line. Let me get rid of my points here. We don't really need them anymore. All right. So in between x1 and x2, so let's go ahead and let's just write the interval x1, comma, x2. Notice that all the slopes of my tangent lines here, I draw one there, draw one there. I can even draw one there. But notice they are all negative. In other words, your derivative is less than 0. They're all negative, okay? And then finally, oh, why did I write -1 over here? This should be x1. I'm really sorry about that. Please, you know what? I turned off comments, so you can't yell at me in the comments. In the last interval from x2, comma, all the way up to positive infinity, notice that all the slopes of my tangent lines are all positive again. So my derivative is greater than 0 again. Okay? Now, how can we use this information to go ahead and plot the derivative of a curve? So I'm going to kind of just like, I got to zoom out here. All right. And here's our example. Given the graph of f of x equals x to the third minus x, plot its derivative. All right. So here's what we know here. First, I know at this point x1, and now I'm gonna go ahead and use red. I know at x1, I have a horizontal tangent. So which means if I just follow this all the way down here, my second graph that I have here, this is going to be x, and this axis is my derivative. Okay. Then if I follow this line all the way down and I put it right here, there is my derivative where it equals 0. Now you got to remember, at what x value, like this second graph is, like I said, the x-axis is x, and the I guess up and down axis, without getting too specific, is our derivative. So where does the derivative equal 0? It's going to be right here at this value right there. Okay. Now you also have another one for x2, so that's going to be right here. Okay. Now look at the intervals that we've created. We have an interval from negative infinity all the way up to x1. All those derivatives are positive, which means on our derivative graph, they're all going to be above the x-axis. So they're all going to be above the x-axis. So they are all positive right here. So sometimes professors, teachers will kind of just do like a line like that and put an arrow. All right. I think that's confusing. What I like to do is just lightly, just kind of like draw a little bit of a line. But the key here is all your derivatives are positive, which means they lie above the x-axis here. All right. Next, in between x1 and x2, our derivative is negative. So the only way that we can go from positive to negative is to cross the x-axis. So it looks like this. All my derivatives underneath here are negative. Now, if you look at x2 to infinity, they're all positive, which means I got to cross the x-axis again. So I know this is going to come down, and it's going to loop back up. And then it looks like this. So here is what the graph of my derivative looks like. All right. Now, just to verify this, okay, I am going to go ahead and I'm going to show you what this looks like graphed in Desmos, because I think that's always really important. All right, so here's Desmos, and notice here we have, I'll zoom in some more. It's too much. There we go. So notice here we have x to the third minus x, obviously, and I said the derivative is 3x squared minus 1. So when I graph the function and its derivative on the same exact xy axis, look what happens. 3x squared minus 1. And notice that at this point right here, you have a horizontal tangent, which means it crosses the x-axis at exactly that point on your derivative. Notice here, down here on the red one, notice here we have another horizontal tangent, which means on the derivative, it should cross the x-axis at exactly the same x value, and it does. Okay? Look at the intervals. I'm just getting rid of all these. Look at our intervals from negative infinity all the way up to this x1 right here. Okay? They're all positive. And if you look, all of in green, all those y values or all those derivative values are all positive. In between x1 and x2, they're all negative, and your green line is underneath the x-axis here. Oh, I'm sorry, my dog is barking. Hold on one sec. All right, I am back, so hopefully that wasn't too bothersome. I used to get real technical and like delete the whole video and re-record it, but I'm over those days. So anyways, Between x1 and x2, all your tangent lines or all your derivatives are negative, hence the green line underneath the x-axis here. And then finally, after x2 to infinity, they're all positive up here. All right. So that is how we go ahead and we take a function and then we graph its derivative. All right. Let's try another example here. Okay, so here's our next example here. Let's find these special points here. So if we just kind of look at this from left to right, we have one like right about here. Let me use a different color. So I'm still in red. So we have one right here. Looks like we have one right about here. And then we have one all the way down here. So the easiest thing to do is just to, like I said, zoom out. And I'm going to move this over into the middle of my screen more. And of course, it didn't take my point. So I'm going to put a point there. One right about there. And then all the way down here. All right. So the easiest thing to do is to come directly underneath. You don't have to be perfect. But go ahead, label your axes x, and then a derivative. All right. And as you noticed before, what I did is I kind of just said, okay, well, my derivative, so DER stands for derivative, is less than 0 in this interval right here. So let me go ahead and just draw this line. And I'm just going to keep this going the whole way down. All right. Now, I know at that point, my derivative equals 0 right there. And then everywhere above or everywhere to the left of this point, of this critical point, all right, that is a critical point. Notice all my slopes are negative, which means they're all going to be down here. Okay? But now, after this point, so between that first critical point, let's call it C1, and the second critical point, C2. So let me go ahead and draw this straight down. I said it doesn't have to be perfect, but notice all your derivatives are going to be greater than 0 because they're all positive. So that means it goes from negative, comes up above, and comes back down here. And it comes right there because your slope of the tangent line is 0 there. Then between C2 and C3, all of your derivatives are going to be less than 0, so they have to come all the way down here until they get all the way over to here. Let me just go ahead and draw this. We know at C3, our derivative is equal to 0, so it crosses the x-axis right there, where our derivative is going to be 0, and then it just comes straight back up, and it looks like this. And that's it. It doesn't have to be perfect, all right? Like if you knew the actual function, you could find its derivative and then type it in and graph it properly, but this is exactly what you would get. All right? So the next thing I kind of want to go over here would be, okay, well, what are some other notations that we use for derivatives? All right? So let's go back over here. Other notations. So you and I are really used to the Newtonian way of describing the derivative, all right, which is f prime of x. Now, this stands for the first derivative, okay? So what that means is if you had a function and you took its derivative, it would equal f prime of x, okay? Another way to write this would just be like y prime. That also is the first derivative, all right? Now, another mathematician at the time, Leibniz, came out with their own notation as well, okay? And here's Leibniz notation. So instead of writing f prime of x, he wrote dy dx, all right? And he called the differential operator he called the differential operator d dx. So all this stood for is just derivative. So dy dx could actually be written as this. D dx times y, which we know if this is y over 1, that turns out to be dy dx. But what this really means is just the first derivative of the function y. Of the function y of x, which is exactly in the upper left-hand corner of your screen, is exactly what Newton is saying. It's just two different ways to write the same thing, okay? Now, there are tons of different derivatives that you can take, okay? Like, for example, and this is where we get into the higher order derivatives. So, if you have a function and it's smooth and continuous, you can continuously take a derivative. So, higher order derivatives. So, for example, f prime of x is our first derivative. F double prime of x will be our second derivative. F triple prime of x, obviously, is our third derivative. And then anything larger than the third derivative, you would just put it in parentheses, and that would stand for the nth derivative. Okay? Now, Leibniz would use a similar notation. Dy dx would be our first derivative. So I'm just going to draw an arrow. Then the second derivative, I'm going to write this one out so you can see it. The second derivative would be the derivative of the first, and this would be d squared y over dx, d dx squared. Okay? So that would be the notation. Let me write this a little cleaner here. This would be the notation for the second derivative. All right? I know it's kind of looks a little weird. In fact, I think depending upon the class, you may prefer Newton's way of writing derivatives versus Leibniz. And differential equations, we end up using dy dx a lot. All right, but anyways, let's continue. So the third derivative is just the derivative of the second. So this would be this right here. There's our third derivative, and then finally the nth derivative would just look like this. Now I know in like old school physics books, the first derivative would look like this with a dot above it. All right, the second derivative would be like two dots and so forth. I've never seen a math book use this notation. The only time I've ever seen it is in like I said, like old school physics books that I would see at like a bookstore or like a yard sale or something like that, and it kind of like caught my eye. All right. So the last thing I want to talk about is how can a function fail to be differentiable? In other words, where on a graph, if you're looking at it, let me write this cleaner. I do that a lot. I have a Microsoft Surface Pro, and I absolutely love this computer. However, sometimes it just doesn't work the way I want it to, and that's fine. But anyways, how can a function fail to be differentiable? All right. Well, the easiest way for me to kind of demonstrate this, all right, would just be some pictures. Okay. So the first one I'm going to draw is right here. And notice here, at that value right there, we're going to call that A, okay? That value has two names, a cusp or a corner, all right? And the easiest way to kind of describe this would be, well, if you think about a tangent line, all right, a tangent line has to be on a nice, smooth curve. Think of like a roller coaster, all right? Well, at a cusp, if I zoom in here, how do you know the tangent line wasn't this? Or maybe it was this. Or maybe it's kind of like a seesaw right in the middle. I mean, you have no idea, okay? So because of that, we call it a cusp or corner, and this is where a derivative would fail. All right, so this is the first case, okay? Now the second case should be clearly obvious. So we call this case, let me label these cases. Case 1, and here's case 2. In case 2, we have a jump discontinuity. Okay? And if you think about it, you cannot evaluate the derivative. All right, the derivative does not exist here because if you're trying to evaluate the derivative at x equals a, which is exactly what this notation is asking us to do, you don't know if you're coming from the left or coming from the right. So if a limit fails, all right, then the derivative is also going to fail. Okay? And then the final case, case 3, is right here. And we call this a vertical. Oh, let me draw a little more. As the kids say, that looks sus. I don't know if they still say that or not. I have no idea, nor do I care. But anyways, I'm talking out loud. I'm thinking out loud. We call this a vertical tangent. And that's because if you notice, our tangent line touches at multiple points throughout that vertical slope right there. All right. So, and we know a vertical slope is undefined. So this would be a vertical, just leave it in red, a vertical tangent. Okay. So just because, you got a function, that doesn't necessarily imply that it has a derivative. Finally, let's talk about this higher order derivative business and its relationship to the world around us. So let me just write this, derivatives. And like I said, we're going to talk about this with the world around us. So if you were to take a physics class, all right, it doesn't matter which one you take, they're all the same. All right. You are given a function s of t. Now, s of t stands for the displacement at any time, and we call that t, okay? If you were to take the derivative of displacement, that will equal v of t, which is our velocity at any time t. If you were to take the second derivative of displacement, which would be the first derivative of velocity, this would equal the acceleration of the object at any time t. And yes, there is a fourth. So let's put it in parentheses. If you can take the fourth derivative of displacement, that will be, excuse me, the second derivative of velocity, which will be the first derivative of acceleration, and that will equal j of t, which is a jerk. And yes, that is technically correct. And hold on one sec. I made an error here. This is just the third derivative of displacement. But the third derivative of displacement is the second derivative of velocity, which is the first derivative of acceleration. And you can see how complicated this can get very quickly. But you get a jerk, and the jerk is how fast or better yet, let me write it like this. The jerk is the rate of change of the acceleration. So you can have an object that is accelerating and you can figure out how fast is it actually accelerating. That's called a jerk. I'm sure there's more, and I'm not aware of them. But if you know, I'd love for you to email me and let me know what they are, and I will include it in more lecture videos. Okay? But this is the relationship that we have. All right? So in the next section or next video, we are going to be doing a lot of derivatives using some derivative rules. And initially, I'm going to just go ahead and just show you what they are, show you some examples. But then we're going to be doing a lot of examples, a lot of like word problems. And within those word problems, we're going to be seeing this relationship come up a lot: displacement, velocity, acceleration. So make sure that you know all of these relationships. So the derivative of displacement is velocity, the derivative of velocity is acceleration, and the derivative of acceleration is a jerk. We really don't see the jerk too much. I hope that's even how you spell it. I'm like 99.9% sure that's how you spell it, but it is what it is. All right, I'm willing to take the L if it's not correct. So you're gonna laugh. This is a complete tangent, pun intended, obviously. I was thinking about like, oh, if there's more, then go ahead and email me about this. But I paused the video and I looked it up, and I cannot believe what I just found. So I'm gonna share. I'm gonna share this with you because I didn't believe it was true. So here we go. So here's a little website here. All right. So we got terminology. We know what a function is. This is great. First derivative is our displacement. Second derivative, all right, is our velocity. And then the third derivative we know is the acceleration. All right. I'm sorry. Second derivative is the acceleration. The third derivative is called a jerk. All right. And I can't believe this. I'm literally laughing out loud here. Here's a nice little table. We got position, which is displacement. Velocity is derivative. Second derivative is acceleration. The third derivative is jerk. And look at the last ones. The fourth derivative is snap. The fifth derivative is crackle, and the sixth derivative is pop. I cannot believe that they are called snap, crackle, and pop. If you are not familiar with that, snap, crackle, and pop is legit the slogan for Rice Krispie cereal, which I just find absolutely hilarious. Like, I had no idea that snap, crackle, and pop, the cereal, is legit the names of the higher order derivatives of displacement, which is just absolutely hilarious. Anyways, I'll let you go. I'll see you in the next video. Bye.